Hello my friends, welcome to the science video and welcome to my very next video where I've again got into the physical chemistry, got into that boring field, and now in this video of my notes I've got the notes of the gaseous state of the physical chemistry. Not wasting my time, not wasting your time, not wasting science time. Let's start, come on. Now, the first thing, effective molecular mass. Nothing but summation of all the masses and summation of total number of moles. Since moles equals mass upon molar mass equals to mass upon moles. Simple fucking conversation for temperature. And now, temperature equals C upon 100, K minus 273, that is for Kelvin. It is this thing, and for Celsius to Fahrenheit, this thing. I hope you know this basic shit. And now going towards Boyle's law, coming towards the gases, coming towards the actual part of this chapter. First comes the Boyle's law, that is pressure is inversely proportional to the asshole volume. So as the volume increases, pressure decreases, or as the pressure increases, volume decreases at constant temperature. This says the Boyle's law. And what about Charles' law? Charles' law states that for any 1 degree change in its temperature, 1 upon 273rd of its volume increases. Don't listen at this basic shit, but it simply says that volume upon temperature equals constant. That means volume is directly proportional temperature. Volume is directly proportional to temperature. It means if temperature increases, volume increases. If volume decreases, temperature decreases, and all that thing. Now, next law, Gay-Lussac law. He was not actually gay, but its name is Gay-Lussac law. So it states that pressure is directly proportional to temperature at the number of moles equals to constant. Of course, volume is constant. Volume is constant. So pressure is directly proportional to temperature. So as temperature increases, pressure increases. As temperature decreases, pressure decreases. This is said by Gay-Lussac, the very good scientist, I hope so. And the next law comes is the Avogadro Law. One with a mighty number of 6.0222 into 10 power minus 23, which is Avogadro. Yes, he is Avogadro. He says that the volume is directly proportional to number of moles. So as we increase the number of moles of any gas, its volume increases. So basic thing. He said such a basic thing, and I hope he got a prize for that. Man, when I could do that, come on, I could do that. Now, Dalton's law of partial pressure. I'm not overacting, guys, so let's get on to Dalton's law of partial pressure. Summation of all the pressure is the total pressure. So basic again. And see what we have right now. P1 is the actually total pressure equals to mole fraction into the partial pressure. Mole fraction upon the into the partial pressure. Okay. Mole fraction into partial pressure gives us the vapor pressure. This is vapor pressure, and this is partial pressure. And we have a small statement down, that is pressure of a dry gas. The pressure of a dry gas equals to the atmospheric pressure minus the aqueous tension, the surface tension. In fluid mechanics I will explain it more. For now you just have to think that the pressure of the dry gas, okay, it is given, especially given dry gas equals to atmospheric pressure minus the aqueous tension. I hope it's okay for right now, but now let's get further to our next page. I'm sorry guys if you feel the notes quite spoily, because I prepared these notes very months ago, or yeah, I think a couple of triplet of months ago I prepared these notes, so I'm sorry, but I hope they are quite informative. Now the next thing we come over is the Graham's law of diffusion, how the gas is diffused. Like if this is a jar, a silly jar, and opening from here It is in the opening of the jar, and we just put a gas. Then how the gas would spread everywhere is told by the Graham's law of diffusion, where R is the rate of diffusion. So R2 upon R1 equals under root of M2 upon N1, that is R1 is inversely proportional to the square root of molar mass. Learn this shit. I hope it's not a difficult formula to learn. So simple. Any rate of diffusion of gas over a surface area or over a volume is inversely proportional to the square root of the molar mass. Okay, and at constant temperature the rate is inversely proportional to the molar mass into pressure. Yep. So I'm sorry, pressure upon the, okay, let me tell you, the rate of change of the ratio of the rate of changes is inversely proportional to the molar mass and directly proportional to the pressure. That is, R1 is directly proportional to pressure upon under root of M1. It's P1. Basic thing. Or rate is distance traveled in a narrative per unit time. Fuck you, asshole. So R equals moles diffused according to the Graham's law. Another basic thing, V1 T2 upon V2 T1 equals under root of the molar mass, or under root of D, where D is vapor density. This is vapor density. So V1 into T2 upon V2 into T1 equals under root of the square root of vapor density equals under root of the square root of the molar mass ratios. Or simple, substituting V by N, N1 T2 upon N2 T1 is equal to the same thing, or X1 T2 upon X2 T1 is equal to the same thing again. X1, X2 are molar masses, N1, N2 are moles, V1, V2 are the volumes. That's the whole thing. Now let's get on to our next topic, a very important thing. And the next topic is nothing but the kinetic theory of the gases. Yes, it is the kinetic theory of the gases. An asshole project. Yes, such an asshole thing. The kinetic theory, as the name suggests, the kinetic energy describing the energy levels of the gas, telling the kinetic energy of the gases depends on the temperature. Oh, I didn't know this. Okay. The pressure of the gas arises due to collision of gas molecules with... Oh, I didn't know that too. Thank you very much for giving me the fuck, Mr. Notes. And PV equals nRT, like that. PV equals to mnu square upon 3, where u is equal to RMS velocity. You learn the formula afterwards. Velocity of gas molecules increases with increase in temperature. Ooh, I didn't know that too. That's so good of you. Thank you, my dear fucking Notes. Okay, so average velocity equals under root of 8 RT upon pi m. So average velocity, we can conclude this thing as, we know that R equals to 8.3 here. So equals under root of 67 something upon pi into RT upon m. No shortcut for this. You have to learn this thing. Fuck this. So under root of 8 RT upon pi m is the average velocity, but we have something for RMS velocity. If R is 8.3, then 8.3 into 3. What the hell is 8.3 into 3? Come on. It's something which is 25. So RMS velocity can approximate it by 5 root of T by m. And by most probable velocity 2 into RT upon m. Oops, I'm sorry. There is no pi here. It's just 2 RT upon m. So it can be approximated by under root of 16 T by m. 16 T by m equals to 4 root of T by m. RMS velocity to 5 root T by m, and most probable velocity equals 4 root T by m. And if someone tells you, hey motherfucker, tell me what is the difference between, or tell me what is the relation between the average velocity and RMS velocity, tell them, bitch please. Average velocity equals RMS velocity into 0.9213. Okay, alright, you have to learn this. You have to learn this bloody number 0.9213. You have to learn this thing. U average or average velocity equals to U RMS equals to RMS velocity into 0.9213. I don't know how the heck is this number, but just simplified by still telling me that average velocity upon the RMS velocity equals to 0.9213. RMS stands for root mean square. Root mean square, let me write it. Root mean square velocity. Types of velocities the gases can project. RMS velocity, of course. Let's get down and down and down again, which tells us about the kinetic energy of the gas. The kinetic energy of the gas is 3 by 2 RT, or is equals to 3 by 2 nRT, yes, or 3 by 2 into PV. Kinetic energy equals to 3 by 2 nRT equals to 3 by 2 PV. Oops, I wrote it here. Kinetic energy for n moles equals 3 by 2 nRT. Another silly formula for kinetic energy equals to 3 by 2 of kT, where kT is not Katy Perry. I know I'm her biggest fan, but it's 3 by 2 kT, where k equals Boltzmann constant 1.38 into 10 power minus 23. You have to again learn this shit. 1.38 into 10 power minus 23 joules per degree. Boltzmann constant. Oh yeah, Boltzmann constant. Oops, my camera. So now this page is over. Let's get on to the next page. That is the compressibility factor. I'm sorry, it's quite wet. There's a leakage of words. So compressibility factor Z equals PV upon nRT. What would you say? You say no, Mr. Science, no. Actually, according to the ideal gas law, PV equals to nRT. So according to this thing, PV upon nRT equals to 1. So please, bitch, PV upon nRT equals to Z, because the gas here is not ideal. And now we got some of the idiotic conditions telling if Z is equal to less than 1, if Z is equal to greater than 1. I don't know does that matters in the real life, but let me say, if Z is less than 1, that means if Z is less than 1 means 1 is greater than Z. That means PV upon nRT is less than 1, that is PV is less than nRT. So hear me right, PV is less than nRT, then the gas is more compressible. Okay, and if Z is greater than 1, that is PV is greater than nRT, then gas is less compressible. I don't know does that matter. Now this thing comes a very important thing, van der Waals equation, we can say, or we can say real gas. Real gas law simply says for n moles, P plus n square A upon V square into V minus NB equals nRT. Simple formula of P V equals nRT. nRT is constant, P V equals nRT, where A and B are constant. In A, in real gas volume of molecule equals B, and pressure constant A. A stands for the constant for pressure, and volume constant goes to B. So P plus n square A upon V square into V minus NB equals nRT is the real gas equation. Simply now we have some of the another idiotic formulas, where P, which is pressure, equals to AN square upon V square, where P equals to pressure lost by gas due to attractions. It depends on nature of gas, of course. It's an experimental constant. If you get any problem on it, then you could get the value of A. And B value is actually 4 into Avogadro number into the volume. Equate this shit, you'll get this thing. And now critical temperature, the temperature above which the gas cannot liquefy. The critical temperature equals to 8 times A upon 27 times RB. A is of the constant which I told you. And simple with critical pressure, A upon 27 B square. Learn these formulas, please. Learn these formulas, please. So critical pressure equals to A upon 27 B square, and critical volume equals to 3B, and critical temperature 8 upon 27 RB. Have a look at them. You can note them somewhere, and you can learn these things. And mean free path, I don't know if that matters to you, but mean free path equals to root 3 by 1 PD, eta root 3 upon PD If you know something about fluid mechanics, eta equals the viscosity, the friction applied by the fluid friction. So eta root of 3 upon pd. And number of molecules of gas in 1 cc, learning factor again, number of molecules in 1 cc of gas, 1 centimeter cube, 1 centimeter square of gas, or 1 cc, the volume, 1 cubic centimeter is 2.617 into 10 power 19 number of volumes. So guys, that's it for now. I hope we completed our gaseous equations, or our the volume and all fucking equations of the gaseous state. I hope you like the video, and if you like the video, then please hit that like button, and don't forget to subscribe, and please please be frank and comment what was wrong in my video, because I want to improve. I want to earn your subscription. I want to become a good YouTuber. So please tell me what was wrong. I would definitely try to improve in my next video. See you soon. Happy sciencing, and hope you learned something.